Good evening to everyone. I welcome you to the second day and third session of the FTP program on computational intelligence and application in power engineering. So our resource person, Dr. Gayadhar Panda, also joined us. He is there. So let me introduce himself. So Dr. Professor Gayadhar Panda holds his PhD degree in electrical engineering from Utkal University in the year 2007. He is currently a professor in the electrical engineering department and entrusted with the responsibility of Dean, Faculty of Academic Affairs from National Institute of Technical Teachers and Training and Research, Kolkata, India. Prior to this, Dr. Panda has served at NIT Meghalaya as an associate professor and professor 2013 to 2017 and 2017 to 2024 respectively. To his credit, he has authored more than 200 research.
Is it audible?
You are audible, but madam is not audible.
Oh, madam is not audible, right? I thought that whether my connection is wrong here.
You are audible, sir. Audible.
Ma'am, your voice is not audible.
Now you are audible.
Ma'am, you are mute. Ma'am, you are mute. Ma'am, your voice is not audible. Rupali madam.
Okay, now it is okay?
Yes, yes.
Yes, ma'am. Yes, ma'am.
Okay, so let me first start from. Okay, so now it is audible?
Yes,
Yes, ma'am.
Okay. So let me introduce Professor Gayadhar Panda. Gayadhar Panda holds his PhD degree in electrical engineering from Utkal University in the year 2007. He is currently a professor in the electrical engineering department and entrusted with the responsibility of Dean, Faculty and Academic Affairs, National Institute of Technical Teachers and Training and Research, Kolkata, India. Prior to this, Dr. Panda has served at NIT Meghalaya as an associate professor from 2013 to 2017 and professor from 2017 to 2024. To his credit, he has authored more than 200 research papers in various peer-reviewed journals and conferences at the national and international level and filed 3 patents. He has also published 1 book, 5 book chapters, as well as served as one of the editors of first, second, and third ISSETA publication in Springer book series. He was invited to deliver over 33 keynote invited talks at national and international conferences, workshops, and training programs. Dr. Panda serves as TPC chair or member of various international conferences. Also, 8 numbers of scholars have been awarded with PhD degrees under his supervision, and currently 6 numbers of research scholars are pursuing their research work under his supervision. Professor Panda was decorated with the prestigious award of the Power Medal IE for his published research work and world's top 2% scientists published by Stanford University in the year 2020 to 2023. He has completed a good number of sponsored research projects on the integration of renewable energy generation and power quality improvement. He is a senior member of IEEE, fellow of IE, and life members of ISTE. Dr. Panda is associate editor for IEEE Access, IETES, Willy, and also serves on the editorial board for the IJEEPS. Recruiter and the technical steering committees for several conferences. He has organized several technical events like IEEE conference, symposium, national workshop, etc. He has delivered several invited talks at various national and international
It's a
events.
PPT size.
His current research interests include automatic generation control stability improvements using flexible alternating current transmission system devices,
इसका
power
size
quality,
छोटा
power
होगा
electronic converter, and distributed power generation. His work involves design, implementation, and operation of AC-DC microgrid with interfacing converters that use digital signal processing, artificial intelligence techniques, and other novel control. So now we'll present Dr. Gayadhar Panda. He will take this session. So sir, please, now this is your session.
Thank you, madam, for your brief introduction. Very good evening to one and all. Am I audible?
Yes, sir.
Hello. Yeah. And whether this PPT is visible to all of you?
Yes, sir.
Okay, fine. Thank you. You can see here, the topic is power management in microgrid system. And my contribution will be here mainly the different renewable energy sources, introductory part. And the second part will be how the converters are coming into picture, means what is the major role in the integration of renewable sources, and a little bit control aspects. Then at the end, we'll discuss why the power management or optimal power management is essential in the microgrid system. Okay. Hopefully, this is a third lecture in this AICT program, as per the discussion with the Rupali Madam. And coming to the basics, you know very well that now we are moving towards the power generation from the renewable energy sources. Why we are going for this power generation from renewable energy sources, that almost you know this, because of the fossil fuels are depleting in nature, with the time frame, we may not find that much of fossil fuels to meet the load demand. In that way, we have to see the alternative sources of energy. And another thing, another major drawback is with fossil fuels that it produces the greenhouse gas emission, and that has to be reduced, because otherwise the climatic change, environmental degradation, all those problems will be coming, and we are also realizing day by day. In that way, the renewable energy sources are the alternative sources, and we should mainly focus on this power generation from renewable sources so that we can maintain our planet, healthier planet. Though under the development of industrialization and urbanization, our lifestyle is changing, but at the same time, we have to maintain our ecosystem also. Okay. Just 1 minute, sorry. उत्पल जी,
सर
बोलिए।
सर वो तेरुजा का सर वो सर भेज दे मेल क्या सर
कौन सा हाँ हाँ
तेरुजा
हाँ भेज
एक बार सुन लीजिए सर उसमें मैं लिखा हूँ we are pleased to inform you that you have been selected for admission to the PG diploma program in human resource management under the Department of Technical Education and Management, Panda, Kolkata. You are requested to report for admission on or before 4 September 2025 within office hours. As the academic section, Panda, Kolkata, along with all original documents, one set of photocopies, and the prescribed admission fees. Please note that failure to report within the stipulated date and time will result in forfeit of your seat. No further request in this regard will be entertained.
yes yes
Carry the following documents. इसमें document जो
ठीक है it is okay, you please send it. Yes. The most important benefit of the renewable energy sources is the fact that non-polluting. Unlike the present sources such as coal and fossil fuels, renewable energy sources are inexhaustible. This means they can be used repeatedly. As we all know that the burning of fossil fuels emits harmful gases in the atmosphere, or you can say that may harm the environment by various factors such as global warming, greenhouse effect, and above all is pollution. These things we have already known, and renewable energy sources are the only the clean energy sources which can reduce these effects. And there are various renewable energy sources that also you know, that wind, solar, biomass, and small hydro also you can think it is coming under the renewable. And the major contribution you can see, if you'll see the data, mainly the power generated from wind and solar. That is the major contribution of the renewables. Other sources are there, but contribution is comparatively very less. This is the contribution of greenhouse gas emission from different sectors. If you see, there are major sectors. One is the transportation sector, electricity and heat, around 42%. Industry sector also 21%. Okay, and these are the main sectors where this greenhouse gas emission is produced. And in that way, you know that now we are mainly focusing on the electrical or e-transportation system to reduce this greenhouse gas emission. This is the world energy production by sources, different sources. Still, we are depending on 30% on the coal. And other sources are there, wind and solar, that is almost equal, 9%, 8%. And these are the sources. We'll move quickly. These are the introductory parts. Okay, where the importance is there, we'll discuss. And this is the solar energy, you know how the solar energy or the solar cell will be producing the power. And these are the rooftop solars. And you know very well, these are the clean sources of energy and that produces the power. And the solar array output is a DC voltage. Then you are using the converters like a DC to DC boost converter, then inverters for integration to the grid. And this is the wind energy. Wind energy operates on a simple principle. The energy in the wind turns 2 or 3 propeller like blades around a rotor. The rotor is connected to the main shaft, which spins a generator.
Sir, sorry to interrupt. Sir,
Yes.
are you changing your slide?
Yes, madam.
But it is not shown. Please check that.
ये चेंज नहीं हो रहा है?
ना change नहीं हो रहा. Please check it.
Then I have to again share.
Yes, now it is done.
Now it is done. Okay, then we will go with this. We are discussing, these are the things. We are talking about the solar energy. Okay. And this is the wind energy. These are the introductory parts. We will not be focusing much. Okay. Geothermal energy. And bioenergy sources. This one is a very interesting area, a fuel cell. Fuel cell is a device which takes the stored chemical energy and converts it to the electrical energy directly. Why I am saying that this is a very interesting area? You might have seen a fuel cell based electric vehicle operation, and this is mainly very stable energy source, you can say, compared to the battery, because once the fuel is available, it acts as a generator kind of thing. That's why it is more means a reliable storage device compared to the battery and supercapacitor, but the cost point of view is comparatively high. This is the hydroelectric energy. It is not required to discuss here in this particular lecture hour. Now we'll discuss here how the power is generated from the renewable energy sources. And you know that renewable energy sources are intermittent in nature. That's why when we design a microgrid or the rooftop solar or any kind of system, we always consider the battery as the storage device so that the power generation will be stable. As per the load demand, you can meet the load demand. And because of intermittent in nature, the storage devices, there are different types of storage devices. Again, those things also you have to think how, which storage device will be best for the application point of view. And microgrid, it is a small-scale power supply network that is designed to provide the power for a small community. You can go for up to the 1 megawatt range, a kilowatt to megawatt range. It enables the local power generation for the local loads, because this microgrid, once we are saying that all the renewables are installed at the load center or the consumer side. It comprises of the various small power generation sources, PV, wind, battery, supercapacitors, and fuel cell. That makes it highly flexible and efficient. It is connected to both the local generating units and the utility grid, thus preventing the power outages. Excess power can be sold to the utility grid. Size of the microgrid may range from the housing estate to the municipal regions. Here you can see the different applications or microgrid, low power microgrid. You can say the medium power microgrid system, high power microgrid system. For residential purpose, hardly we are going for the 5 kilowatt power. Similarly, medium power for the data center. And for an institute campus, or you can say the industry, that is the range of 1 megawatt range you can think of. And when we talk about the microgrid system, many sources will be integrated. Storage, many storage devices will be integrated. Electric vehicle also come into picture. So many things, and this microgrid can be connected with the utility grid, or it may be operated at the standalone mode by means of this bypass switch. And there are different kinds of the classification of the microgrid. One is the AC microgrid, DC microgrid, and a hybrid AC-DC microgrid. When you talk about AC microgrid, that indicates that your available voltage and frequency, it will be there, and so that you can connect the AC loads. Like in general, you can see all the loads are in AC. That means they will be operated in AC supply. And when we talk about the DC microgrid, your bus voltage is DC. You can connect the specified or the designed DC loads. Nowadays, you can find the DC fans, DC fridge also. It is operated with the DC supply. Because why we will go for the DC microgrid? It has major advantage from the control aspects, and complexity is very less compared to the AC microgrid. And when we talk about the limitation in case of DC microgrid, because in general the loads are designed for the AC, and when you want to connect all those things, then you have to again go for the inverter, so that you can connect the AC loads to the DC bus via inverter. And when you go for the hybrid AC-DC microgrid, it is a combination of AC bus as well as the DC bus, so that the DC loads directly connected to the DC bus, and all the AC loads can be connected to AC bus. But the complexity of control mechanism is comparatively more here compared to either AC or DC microgrid. And when you integrate the renewables, or you can say that if you generate the power, maximum power you can say, with the renewables, then there will be so many practical difficulties or challenges. Because as I told you at the beginning, and all of us know, these renewables are intermittent in nature. That's why the power generation is not a stable one, and it is fluctuating in nature. And in that way, to make the stable operation, we need to have the battery storage systems, and it should be operated in the grid connected mode. Those things are to be taken into account. And another thing is that when we integrate the renewables, and that time your conventional power plants and the generators, number of generators, all those things will be reduced. In that way, the inertia is a major issue. When the power generation will be from renewables will be there, then the inertia is a major issue. Then the stability problem also arises. In that way, you might have done so, maybe you might have heard or you might have done the work also in virtual inertia. And other factors are there when you are going for the integration, and converters, inverters are used, and those are the static devices, but produces the harmonics into the system, because those switching devices are nonlinear in nature, and that way the power quality issues will be also arise. Whether I am audible and slides are moving?
Yes,
Hello?
sir.
Yes, sir. Yes, sir.
Okay. Because we are moving with the basics, I think those who are at the beginning level, they can get to know. And slowly we'll explain what is the power management of those things. As I told you, the energy storage devices are very much important here, and there are various devices like battery, flywheel, supercapacitors. And here you can see that how you will select or energy storage system depending on many factors, you can say. Okay. All electrical energy storage systems have the same basic components: interface with the power system, power conditioning system, charge or discharge control, and the energy storage medium itself. Each storage medium has different characteristics: energy density, charge or discharge time, effect of repeated cycling on performance, and life, cost, maintenance requirements. Available energy storage systems: batteries, superconducting magnetic energy storage. These storage devices are mainly used in the industry. High-wheel energy storage, high maintenance cost. Supercapacitors. These supercapacitors or ultra capacitors are used mainly to take off the, means mainly to maintain the power where the fluctuation of load is instant in nature. The use of battery system, that is with the grid, is well known. There are several types of the battery. Yeah. And that is used for the different applications. And now lot of research is going on in battery management system, how to minimize the cost, size, and how you can maintain the charge, lifetime, so many things. Health of the battery is also one of the factor. And depending on these are the parameters, you can select the size of the battery, longevity, which points are very much important for your application. In that way, you have to select the battery. Supercapacitors, as I told you, that the supercapacitors technology stores the electrical energy directly between the two electrodes rather than the converting the charge to another form, such as mechanical energy in case of flywheel or chemical energy in case of batteries. That is the major advantage. In that way, the time constant is very less compared to the battery. Here the question arises whether the supercapacitors replace the battery. That if you see in many applications, you will find the combination of the supercapacitor and battery is a best choice instead of going only with the supercapacitor. Then what is the difference between supercapacitors and batteries? There are four main differences between the supercapacitors and battery: energy density, power density, lifetime, and cost. Energy density. Energy density refers to the amount of charge a technology can hold. Supercapacitors have the greater energy density of any capacitor technology, but batteries are far superior than the any capacitor in this category. Batteries store charge chemically while capacitors store charge electrically. Chemical reactions have the capability to store much more energy than the electrical storage, which is what contributes to batteries being used more often in applications that require the higher storage. Then for applications where the higher storage is required, we should go for the battery. Otherwise, we can go for the combination of battery or supercapacitor. Energy density is high in case of battery compared to the supercapacitor. But case is reverse in case of a power density. What the power density says? Power density refers to the amount of time it takes a technology to charge and discharge energy. Batteries have the disadvantage in this characteristic due to the chemical reactions that takes place to store and release the energy. It takes more time compared to the supercapacitors. Supercapacitors have the faster charge and discharge rates than the batteries because the chemical reactions that takes place within the batteries longer time to release electrons than the electrical discharge in supercapacitors. And if you come to the lifetime chemical reactions are the limiting factors for the lifetime of the battery. That means lifetime is comparatively less in case of batteries with respect to the supercapacitor. But where the cost is high in case of supercapacitor, if you will be selecting the same rating of the supercapacitor and battery, you have to pay more in case of supercapacitor. Here we are talking about the fuel cell, why it is so reliable. You can see the fuel cell is an electric power generating unit that converts the chemical energy of hydrogen, etc., into electrical energy using the principle of electrochemical generation. The fuel cell produces power through a chemical reaction, and energy is released from the hydrogen when it reacts with the oxygen in the air. And these are the fuel cell stacks. You can increase or decrease the rating of fuel cell by choosing the number of cells. And what is the biggest difference between the fuel cell and battery? The biggest difference between the two is that a battery stores energy while a fuel cell generates energy. That is the major difference by converting the available fuel. A fuel cell can have a battery as a system component to store the electrical energy. That means if the additional power is there, that can be stored in the battery. The electrical energy content within a battery is either from the factory where it was made or from the charging the battery by an outlet. This is not required. A fuel cell is different. It takes an energy source such as propane, diesel, or natural gas and converts it into the electrical energy. Here you can see the comparison between the different storage devices, that is the energy density and the power density. In that way, a fuel cell is a more reliable storage device. This is just a small idea about the smart grid. We are talking about we are moving towards the smart grid system. When you will integrate the digital and the information system into the power grid, it will be termed as a smart grid. We are talking about the smart microgrid nowadays because a lot of control and power flow, information flow, everything is taken into account. Digital communication is there, and in that way the decision is made at the control center. In that way, we are moving towards the smart microgrid system or the smart grid system. And there are various challenges will be there because a lot of issues will be there. We can slowly move towards the smart grid system because the problem is that what the conventional system is designed, that particularly the transmission distribution system, considering that power flow is unidirectional in nature. Power is generated at one remote locality and then it was transmitted, then distributed towards the load side. And it was assumed that the power flow is unidirectional from generation to the load side. And accordingly, the relay, switchgear protection devices, all those things are designed accordingly, and transmission line is also designed that way. But when we will go for the predominantly the usage of the renewables, then these renewables are distributed in nature, and we are putting it in to directly at the load side, then definitely there will be a bidirectional power flow, and only the consumers will be the active consumers, we can say, that they have the option when the smart microgrid or smart grid concept comes. The consumers have the option to sell the power as well as purchase the power as per the requirement. And there are a lot of issues will come, and dynamic tariff will be there, and at what point of time you will sell the power, at what time you will purchase the power, so that you will be more beneficial. All those things are in the research papers so far, but we'll see that how far it is implemented in the reality. Definitely, we are moving ahead. And how you will think of a microgrid system, as I told you, if it is a PV array and it is a low voltage output at the PV array, and you cannot directly integrate with the main power supply or with the grid, because you have to match the voltage. And in that way, this voltage is boosted out by means of a boost converter. And then after that, it is converted to AC by means of the inverter circuit, and your inverter output again, we have seen that it will conventional inverter or without any control strategy, you will find the output voltage is a rectangular output voltage, not the pure AC. That's why the control is very much important, because the inverter output should be pure sinusoidal with nominal voltage and frequency, rated voltage and frequency, so that it will be synchronized with the grid. In that way, the converters, DC to DC converter, inverters, and control strategy is very much essential when you are designing or developing a microgrid system, either at the laboratory scale or you can say for the research purpose. But design will be design parameters, all those things also you have to see into account. We cannot take the PV array at the randomly also, depending on the load conditions, all those applications point of view. You can design the different parameters as well as the ratings of the DC to DC converter and inverter. And for that, one of the literature paper is available, that is published by Prof. Sir. And in that way, all the parameters, how to decide all those things, it is mentioned in detail. The DC link, voltage selection, grid coupling, inductor, all those things are written in that literature. This is a microgrid system that we told. And when we design a microgrid, this should be in a position to operate in both grid connected as well as in islanded mode, and accordingly the control mechanism will be different. Here you can see in case of a grid connected mode, once grid is there, lot of issues will be taken up by the grid itself. Then only the main objective will be that what is the power available at the solar side or at the renewable side, we should try to push that power towards the grid as well as the load. Okay. And your inverter will be operated at the current control mode in case of a grid connected operation. But in case of islanded mode or a standalone mode, if the microgrid is standalone mode, what will be the problem? Here the microgrid is at the standalone. That means your output voltage and frequency should be maintained at the nominal value. Then voltage is very much essential. Otherwise, the loads operation will be in fluctuating, or you can say that the loads will not be operated properly. In that way, you have to maintain the voltage at the nominal value. That's why in case of islanded mode of operation, the inverters will be operated under the voltage control mode. And there are few papers you can see that seamless operation of microgrid system. That means the microgrid system can be operated either in grid connected or standalone mode. In those applications, seamless transition, there a lot of things will come into picture. One is the islanding detection. Then once it is determined that the grid is out from the microgrid system, then this changeover takes place from the current control mode to voltage control mode. Then only we can say that it is a seamless operation of a microgrid system. We have also 1-2 papers in that direction. This is the operational modes, that is grid connected mode and islanded mode. Then what I have told, that if the converters and inverters are the very important devices for integration of renewables with the grid, then we should have the basic knowledge about how the inverters are working. Okay, here we'll give little bit idea, and much more work you will find with the multi-level inverters. Now a lot of research is going on in the design of a multi-level inverter for renewable energy applications. because we are moving from the conventional inverter to multi-level inverter, particularly to reduce the harmonics in the system. And we can integrate with the high level of renewable energy sources. Then what is the major advantage of PWM inverter compared to the only inverter? Any one of your participant can say something? What is the major advantage of PWM inverter? Because we should check whether participants are there or simply because we organize various training programs. Sometimes we don't find anyone that responding. Okay, because the connection we may find that so many participants are there. Yes, any of you who are really from power electronics area, can you please say something that what is the advantage of PWM inverter? Pulse width modulated inverter. No.
Sir, my area is power
No,
electronics.
no,
I
no,
work.
no, I will not expect any answer from you. I want to
Yes, sir.
see
Yes.
that how other participants are really actively attending that way. Okay.
Yes, sir.
Otherwise, this is only to cover up my task and 1 hour, 30 minutes, I think. Yeah.
Sir.
That should not happen, but at least 10-20% if they can interact with me, then it's a
Mm-hmm.
good thing.
Yes, sir.
Anyhow, this is a three-phase inverter, current source inverter, and there are different PWM techniques, and it has advantage as well as disadvantage also. It will go for the single pulse width modulation. It will analyze the harmonic content is more. Then we are jumping towards the multi-level inverter. Okay, and because these are the rectangular output voltage from the single phase inverter, and you can calculate that harmonic content by using the Fourier series. And here the harmonic content is more. And next part, because of reducing the harmonic content, we are going for the multiple pulse modulation technique. Here the number of pulses over half cycle, and accordingly, if you will derive the Fourier series, you will find that comparatively less harmonics. Okay. And similarly, again, you can reduce the harmonics by going for the sinusoidal pulse width modulation. And you know that how the pulse width is generated by comparing the two sources. One is the reference signal, another is carrier signal. That way, the number of pulses, number of pulses, all those things you have to see depending on the frequency of the carrier signal. And what is the modulation index? That also you know that modulation index is the ratio of peak magnitude of the modulating waveform and the carrier waveform. That is the reference waveform to the carrier waveform. And modulation index controls the harmonic content in the output voltage. And this is a trapezoidal wave modulation. And there are so many modulation techniques like space vector modulation and other modified space vector modulation. Many modulation techniques are also available. And mainly the idea is to how to reduce the harmonic content. Yes, we are talking about multi-level inverter. Why we will go for the multi-level inverter? Here you can see upper one is a two-level inverter, that is a conventional inverter circuit, and here this is a 5-level inverter, multi-level inverter. And if you will see, it is a staircase output you will be getting. But in the 2-level inverter, it is a rectangular output. And if you analyze the harmonic content in that output voltage, definitely it is less in case of a 5-level inverter. That's why the main focus or research is on the multi-level inverter. Here, what are the key features of the multi-level inverter? You can see low harmonic distortion content, multiple voltage levels at the output, can eliminate the use of filter circuits, because when the harmonic content is less, you can design the filter circuit accordingly, the size of the filter will be reduced. Can operate at both output frequency as well as supply frequency. And what are the issues? Requirement of the more switching devices, more cost, more complexity. That's why so far it is in the research level, but in commercial application, it has a limited space at this moment. Then multi-level inverter-based power conversion system. This is a one laboratory prototype we have shown. We have done the work here. One of the PhD student he has done the work with the multi-level inverter. You'll find many papers with multi-level inverter that is published by our one of the scholar, Dr. Kabila Prasad Panda. These outcomes, you can say that this is a laboratory prototype, and this is also the work taken from the one research paper. These are the different outputs with the different configurations. Then now we are coming to the important aspects, which is the power management and control in microgrid system. The question arises, why we will go for the power management? If you'll see, at the beginning, we did some work with effective power management. What is that effective power management? Then slowly it came to that optimal power management, all those things, why it is essential. Any of you are doing the work in power management area? Optimal power management. Because when we talk about microgrid system, we have already told that many sources will be there and many storage devices will be there, and that can be operated either in grid connected mode or in the standalone mode. And accordingly, you have to think, if it is in a standalone mode, there are two sources are there. One is PV and another is wind, and two storage devices are there. Like a fuel cell is there, battery is there, and it is in a standalone mode. Then how you will maintain the power allocation, okay, so that you can meet the load demand. And sometimes in case of a standalone system, it may not be possible with the existing sources and storage devices to meet the load demand. In that case, you have to go for the priority based load, and you have to connect priority based load, and a few loads will be disconnected. In that way, so many things will come into picture when you are operating in standalone mode. And our main intention is you should generate the power with the effective cost or minimum cost. Cost of operation should be minimum. That is the major objective in case of power management. Because if you have the two sources, two storage devices, and and load is a variable one, you have to think that who will generate at what amount of power to meet the load demand, so that the cost of power generation will be minimum. That concept is very important, and accordingly many papers you will find in optimal power generation and control. Here you see we have taken one DC microgrid system, and it is operated in a grid connected mode. And this is also a published paper in IEEE. And here the PV, supercapacitor, battery, fuel cell based DC microgrid, and loads are also connected. And here we have not used the optimal power management, but we have claimed that it is a effective power management considering few points. We have not applied the optimization technique here. Okay. What we did, these are the independently how it is operated, it is shown, and we did that work that time. It is long back, maybe around 7-8 years back or 10 years back. Okay. That this is a work done by a MTech student using the Xilinx model, fuel cell based DC microgrid system, then fuel cell and supercapacitor based DC microgrid system, and it is operated with the Xilinx modeling. Okay, these are the results. And here we have taken that what we told that effective power management. We have taken the mainly the SOC minimum and SOC maximum. Considering that we have taken few cases, and accordingly the microgrid was operated. And we cannot claim that that is the minimum operating cost, but it is a stable operation with the effective power management. Here you can see that at what point of time, if the load is suddenly increased, that time the supercapacitor comes into picture. And when the load will remain for a long time, that time the battery is coming into picture. That concept we have taken, and so that the operation will be in such a way that there will be the battery and supercapacitor should not go below the SOC minimum, and it should not be also overcharged. It should not go beyond the SOC maximum. In those cases, we have simulated and published this work. That time it was just initial stage of power management. That's why it was published in a IEEE transaction. Now a lot of so many papers are there. This is a grid-tied self-reliant DC system, DC microgrid system. And this next part is the optimal power management system. When we come to the optimal power management system, what we did here, the objective of energy management system is to supply the demand load from the DGs and ESS and the utility grid with respect to an optimal economic technique to minimize the operational cost. There are many input variables to the EMS, which includes the load demand, PV and wind turbine power output, system constraints, SOC of the battery, operational and maintenance cost of each DGs, and energy storage system and the grid tariff. Here you see for each sources we have written the cost factor. The output power of the PV system changes with the weather condition. The power generated from the PV at hour time t is calculated as follows. Okay, we have taken this work also from published paper. Okay. And this is the solar power. And for wind model also you can make the wind model. This is also available in the literature. And for every unit we have to make the model, and after that you have to make a objective function. Here you see, this is the objective function f of x. Taking all the cost functions, you have written the operational cost, that is f of x. And our objective is to minimize this operational cost with different constraints. There are so many constraints also. What are the, there may be equality constraints. That means sum of the power generation should be equal to the load demand, because we should generate the power so that the load demand will be met. Then only it is a stable operation. And there are different constraints, force constraints. That means you cannot go below the PV minimum and PV maximum. That is a source constraint. For PV, wind, and storage system, again the SOC minimum and SOC maximum, these are the constraints. Then once you know the constraint, this is a constraint optimization problem. You have to optimize or minimize the operational cost with the equality constraint and inequality constraints. And to solve this kind of problem, it is better to utilize the optimization technique, heuristic optimization technique, or there are many optimization techniques, combination of all the algorithms. We'll discuss little bit on the optimization technique like GA algorithm, genetic algorithm. That is also a randomly sort algorithm, heuristic algorithm, you can say. And you know the different steps, how the genetic algorithm is applied. Okay. And this is also a natural process of refinement. And genetic algorithm are a search and optimization technique based on the Darwin's principle of natural selection. And here the main idea is select the best and discard the rest. Okay. And its working mechanism will be, you have to initialize the population size, and then you calculate the fitness function, and based on the fitness function, if the objective is reached, then the program will be terminated. If not, then again you have to go for the selection, reproduction, crossover, and mutation, and number of iterations will be increased accordingly. You have to give the termination criteria also depending on the number of iterations, or your any other convergence criteria if you provide, then the program will be stopped. And this crossover is nothing but it is the process in which the two chromosomes, these are the things you know very well, because you have to select the chromosomes, and you can go for the single point crossover or 2-point crossover. Then it is a randomly mixed kind of thing. Here you can see that this is a single point crossover, and similarly you can go for the 2-point crossover also. Means when you will go from one generation to another generation, you should find that yes, improvement is going on. And mainly what are the advantages over the conventional optimization technique, that you know also, because this technique is mainly used for the global global minima or global maxima, and at the same time the for the nonlinear functions. This is the crossover. And again another parameter is the mutation. It is the process by which a string is deliberately changed so as to maintain the diversity in the population set. And this is the offspring. You can take the offspring and accordingly you can change depending on the probabilistic. You can change that at the two places or the more than two places. Accordingly, the computational burden also will increase. These are the advantages of the GA, that is the global search methods. GA searches for the function optimal starting from a population of points of the function domain, not a single one. This is a blind search method, no doubt, and what other advantages? It is a parallel machine since the real world design. Okay. Then we have told you there are so many other optimization techniques like particle swarm optimization, then many recent techniques like Joya, so many ant colony. Only the problem is that you should be in a position to formulate a problem, that is the cost function. Once that is done, then tools are available, optimization tools we can utilize and can find the allocation of the power or optimal power generation. And these are the few research papers. Many other papers are there. You can see our institute website or Google Scholar, so that you can read our papers if you are interested in any particular domain. We have explored particularly in the multi-level inverter as well as the seamless transition of microgrid system, DC microgrid, and now also one of our research scholar working in a high gain converter for EV operation. And power quality analysis also we have done, that is the monitoring and control of microgrid system. All those areas we have explored, and if any of you interested, you can see our papers. If you see my presentation will be very much basics level, and I know that it is in the evening hours, and many participants are only simply attending the program. And anyhow, I have covered the different energy sources and why it is very much important to move towards the power generation from renewable sources, so that it is our foremost duty to maintain the planet healthier, or the future generation they should lead their life better. Though we are in a developing countries, it is our responsible to go for the power generation from renewables. If we, all of us will be little bit think about this, maybe with the near future we'll find better life compared to present life, how the climate changes are creating a problem. Sometimes you will find rain, sometimes it is too hot. A lot of difficulties we are facing in the summertime also. And those renewable sources, and now we are talking about the e-car, e-vehicle, and mainly focusing on the fuel cell based electric vehicles. That is also another research area, and we can think how to get the power generation from fuel cell. And we talk little bit about the different converters like the multi-level inverter, and what is the basic difference between the conventional inverter and the multi-level inverter to reduce the harmonics. And next part we told about the optimal power management. Why we will go for the optimal power management? Because randomly we should not generate the power. We have to see that the operational cost to be minimized depending on the combination of sources and storage devices. All the time storage devices are not required to generate the power. Which one will be minimum, that accordingly we have to think. And load is a variable. Sometimes we have to generate the power from both the sources and both the storage devices. And last part we have told that we have few papers, published paper, and if anyone is interested, you can see our Google Scholars. This is all about from my presentation, and now I will request anyone if he's have any interest, they can interact with me, or they can put the any question. Rupali madam, I will be
Sir.
now interaction time because I have some other work, and if the participants are there, they can put the question because it is just a basic lecture.
Yes, sir.
Uh,
So, dear participants, all are requested if you have any queries related to the topic, you can ask sir. As sir covered very basic thing of the power and its
Power management in
power
microgrid.
management. Yes.
Good
So,
evening. Hello. Good
Yes,
evening.
yes, please.
Sir, I'm from Kolkata.
Very good.
I have already completed a short-term training course at from NITTTR Kolkata under Soumitra Kumar Mondal sir 2000 at 2000 also.
Very good. You are from which institute?
I am from Elite College of Engineering, Shodhpur.
Okay. Yes.
I am pursuing PhD from Jalapur University.
Oh, pursuing.
Yes, sir.
Okay. In which area you are pursuing?
I am in machine in drives.
Machine drives.
Yes, sir.
Electric drives.
Drives.
Okay.
I have a question about SPWM inverter. You have just discussed about the mitigation technique of harmonic in SPWM inverter. So I have a question that what is the best technique, third harmonic injection or selected harmonic injection, which will give us the optimal result?
Which one is the?
Which will
Yes,
give
yes.
us optimal result in case of harmonic elimination?
You see, our major objective is to reduce the lower order harmonics. Okay. That's why we are thinking of different techniques, PWM techniques.
Okay.
Because once you are able to reduce the lower order harmonics, then it will become more easy to filter out the higher order harmonics. And in that way, we are moving towards the different control techniques, PWM control techniques.
And
but, your question is which one is?
Which one is optimal solution? Will give this optimal solution in case of third harmonic injection technique or selected harmonic elimination technique?
That I have no idea. Rupali madam, if you can answer this question, it will be better. What is his question? Rupali madam, are you?
Yes, sir.
Able to understand this question? What he is asking?
So he is asking that different types of actually harmonic injection techniques are there, like third harmonics injection, fifth harmonic, like that. So which PWM technique is best to get this result? Means which is now means whatever the research said, which PWM technique we have the best result regarding the harmonics mitigation, like that.
Actually, third harmonic injection technique and selective harmonic elimination technique, which will give us the
Optimal result.
micro.
Yes, yes, yes. Optimal result means optimum TST where we got.
Yes, with respect to total harmonic distortion.
No idea. No idea, Mr.
I'm Snesh Sharma.
Okay, Mr. Sharma.
But sir,
Any other?
as per my research, I can say
Yes.
that second technique, which is the
Selective harmonic elimination.
yes, 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 selective harmonic elimination has given the best result than the third harmonic injection. Because in case of third harmonic injection, we are able to completely eliminate the third order harmonics, right? But in case of selective harmonic elimination, we can select the different types of lower order harmonics which are normally harming or harmful to our system.
Means
So in that
multiple
case,
harmonics you can
yes,
eliminate.
yes, yes. So in that case, we are able to minimize the lower order harmonic successfully. So overall
Okay.
TST got
THD will be reduced. Okay,
yes, yes,
okay.
yes,
In case
yes.
of third harmonic injection, actually third harmonic is the main process or process in case of our total harmonic distortion. First of all, eliminate the third harmonic, then the waveform will be better. Am I
Yes.
right? So that selected harmonic elimination, in case of selected, then you can eliminate harmonic 7 and other odd harmonic like that. Okay.
Yes, sir.
Okay.
So that third harmonic injection technique more harmonic elimination better than third harmonic techniques, third harmonic injection technique. Am I right?
Yes, yes, you are right. You are doing research means a lot of things you know. Right? Because your research area is particularly in that domain.
Thank
You are
you.
right, Mr. Sharma.
Yes, sir.
Yes, you are right. Any
Thank you.
other? If there is no queries, then we can wind up.
Okay, sir.
Huh?
Okay. Okay, sir.
Okay, thank you.
Thank you, sir.
Thank you.
Thank you, sir, for an insightful session on power management in grid integrated hybrid system. We truly appreciate your time and expertise. Thank you once again, sir.
Thank you, sir.
Thank you, madam. Now I can leave this
Yes, sir.
meeting.
Yes, sir. Yes, sir. You can leave. Okay. So, good evening to all, dear participant. Please take a minute, take 1 minute or 2 minutes to submit the feedback for this session. Your inputs are essential for continuous improvement of this FDP. Okay, so kindly take 1 or 2 minutes then to submit the feedback for this session only.
The attendance link I have sent here. So the participant, those who are present here, can open that link and give only put P if you are present. That's why I'm not sending this in the WhatsApp group. I'm sending only here. So those who are present, put a P. Then I will match with my tracking system.
Madam,
Good
it is,
evening. Ask your request
you
asking.
need access. It is showing it is you need access.
It is not given the access.
No.
One second. Okay.
No.
Once again, we will send. Okay.
Okay, one second. We are sending. Just wait for a minute.
Okay.
Okay, now you can check this link. Is it okay now?
Ma'am, in phone we cannot
Yes, sir.
get the link.
Okay, no issue. It is a secondary link that we are collecting. I have also the tracking system. I can track the attendance, but it is for the just those who are present and attending. And now I'm requesting all of you to switch on your video so that we can take a screenshot. All the participants are requested to switch on the video, please. All the participants, please switch on the video. Snehesh sir, Susri Sangeeta ma'am. Yes. Chandni madam, please take a screenshot. Chandni madam. Hello. Chandni madam, is it audible? Chandni madam. Evita madam, are you there? Hello.
Ma'am, I have taken the screenshot.
Okay, thank you, sir. Thank you. Okay, so all of you are requested to stay tuned. Our next session will be started soon. Yeah, Prasantini madam, hello.
Ma'am.
Did Sujit sir join?
Yes, sir. Ma'am, I have called to Sujit sir, and he
Okay.
told that he will join after 5 minutes.
Okay, okay. So stay tuned.
Hello.
Yes.
Madam,
Yes.
Madam, that attendance and feedback will be sent in the WhatsApp group or not?
No, this attendance link will be only sent in this meeting only. It will be not sent in the WhatsApp group. The feedback will send in the WhatsApp group.
Feedback not sent yet.
Okay, we will send it. Don't worry, we will send it.
But attendance once will on our video, then it will be taken automatically.
No, no,
As you were saying.
I have the tracking system. Those who are attending the session, it is tracked automatically.
Okay, one more attendance is there. All of the participant is showing there. No option is there. You can get that from the people. Okay.
Yes.
Madam, I think no need to switch on the video. All the participants are automatically shown at the people. Those
No,
are
no, no.
done.
Actually, sir, we are uploading the photo of every session in the Atal FDP portal.
Okay,
That's
then.
why we need to take the photo. Yeah.
Okay, right,
Okay.
right.
Okay, sir. So, Prasantini madam, Sujit sir has joined. So, please introduce himself and we will start the session.
Yes, ma'am. It take 2 minutes. Then I will start. Okay.
Okay, ma'am.
Okay, good evening to all. Sujit sir already has joined in the session. I think all of you have finished your feedback session. So we move to session 4. Um, good evening, sir. Good evening, sir. Sir, are you there? Sir, your voice is not audible.
Am I audible right now?
Yes, sir. Yes, sir. Now this is audible. Okay. We are privileged to welcome our esteemed resource person, Dr. Sujit Kumar Bhuyan, Assistant Vice President at Manikaran Analytics Limited, Delhi, and Associate Professor at BIET, Odisha. He will speak on control and power management strategy of grid-connected hybrid energy system. Dr. Bhuyan has over 18 years of experience spanning academia, industry, and research at Manikaran Analytics. He had a team of experts in solar, wind, SCADA, and MIS operating, specializing in renewable energy forecasting and scheduling. He holds a PhD from KIT University with BTech and MTech from BPUT and has earlier worked with IIT Guwahati, IIT Indore, and Highest Private Limited, Bangalore. His expertise cover hybrid renewable energy system, microgrids, optimization algorithm, data science, and cloud technologies. Dr. Bhuyan has published more than 25 research papers, guided PhD and postgraduate scholar, and authored a book with Lambert Publication. We are honored to have him with us today to share his knowledge and insight. Sir, I warmly invite you to begin your session. Sir, this is your session. You can now take.
And good evening, everybody. Am I audible?
Yes, sir.
Okay. So my topic is modeling and simulation of
Sir, it is mute. So please unmute
hydrogen.
yourself.
Now the
Hello.
yeah, am I audible?
Yes, sir. Yes, sir. Now it is audible.
Yeah. Okay. Right now, in the industry, hydrogen energy also going so much of fast. So I'll just show you the how the hydrogen energy will be work on that. Also, hydrogen is divided into two types: in the green hydrogen and the blue hydrogen. Just I'll brief about that. And already the Prasantin already told me that here in this session, whatever the work I have doing right now in means the company in Manikaran Limited, the artificial intelligence and machine learning, what the things we are doing on the load side and the generation side, also give some description about that. Also, I have just told about that. So first of all, we go for the topic. For the topic I have assigned, the modeling simulation of hybrid energy system connected to the grid. So in the hybrid energy system, I have taken here first of all the solar energy, then battery energy system, then hydrogen energy system. I have taken the three type of energy system. As well as I have give some idea about the wind energy also. So here just a minute. Yeah, Prasantini, it is not scroll off. I think what happened to? Okay, what happened to? I cannot understand. It is scrolled right now.
Yes, sir.
Okay. See. So this is the overall simulation model. Whatever means we have designed and I have worked on that. So see this here. Some PV panel will be there. PV panel is there, and across the PV panel, I have used the boost converter. So I think everybody has knowledge about the boost converter. The principle of the boost converter is it converts the low DC to the high DC. Means we can say that in the step-up transformer, we can convert the low AC to the high AC. The boost converter work this type of thing in the DC case. So here PB connected is the connected to the boost converter with the help of MPPT. And I think all of you have idea about the IGBT circuits, MOSFET circuits, right? So IGBT switches, MOSFET switches. So here I have used the IGBT switches, and MPPT is used to trigger the IGBT switch. Okay, so this is the PV system, and here some battery system I have used for the when the PV system is failure, when the PV supply is not available due to the various weather conditions, then battery and the auxiliary unit will be formed there. So I have used the battery energy systems. So in the battery energy system, I have used the buck boost converter. The buck boost converter here, the work is it converts AC and DC on both sides. Means it buck. Buck means it converts the high voltage to the low voltage, and a boost matlab it converts the low voltage to the high voltage. So it works on both directions. And basically, why I am using the buck boost converter in the PV system? Because of battery, and battery is used to the discharge and a charge, right? So due to this two types of activity, I have used this buck boost converter. When the battery SOC level, SOC means state of charge. So state of charge is low, then it is usually to charge the battery. When the battery is overcharged, means around 90% above the charge is there, and the PV connectivity will be the low, and demand is more, then it is used to charge the supply the power to the load, right? So that's why I have used the buck boost converter here. And auxiliary unit, you can take as the temporary unit. When I have my principle here, when the PV and the battery is absent, then I have use the battery, and at that time the auxiliary unit will give the supply of the required amount of power to the load. Okay, so in this figure I have described what the connectivity will be there in the PV system, battery and auxiliary unit, and the connection. So basic thing is how the microgrid system is connected to the grid, right? This is the basic principle and basic fundamental. So basically we are using three type of connectivity: either common DC bus system, either common AC bus system, otherwise both common and AC bus system. So in the two manner we can use the grid connection, the DC bus system or common AC bus system, or both common and AC bus system. So basically here I have used the common DC bus system. Means if I'll use the wind energy, if I'll use the PV, battery and all the, first I have converted into the common DC. After that, I have converted into this DC to the AC. And in the common AC system, all the systems, means wind case, you can say the wind, we can say the battery, we can say the auxiliary unit, so we can say the hydrogen energy. First of all of you converted into the common AC. After that, it is to the common AC bus system. Then it will inject to the power to the grid. So, this basically we are using these two type of techniques frequently. But DC is quite easy, and control on the DC is little bit easier rather than AC. And all of you know that the frequency concept will be the AC system. So the control of the frequency is more complicated than the DC. So DC has no frequency concept. That's why basically we are using the common DC bus system. And in the point of cost, we can say that DC is most costlier than the AC. Why? Because of power to devices. So most of the we are using the pulse width modulation, more power-rich devices, just like I have given you the example of DC-DC converter, buck boost converter, boost converter. These are the converters, DC-DC also, and we also use the pulse width modulation, voltage source inverters, and these are the power transmission, and these are the most costly equipments we are using. That's why. Common DC bus system is more costlier than the common AC bus system. Yeah, Prasantini, I am little bit faster or I have to make slower one. Hello? Hello? Hello, Prasantini? Am I audible?
Yes, sir, you are audible.
Yes, sir, you are audible.
Okay, okay.
Yes, sir.
I'm little bit faster or means I have to make some slow manner, go for the slow manner.
So it is right.
Okay, right. Okay, thank you. Just means tell me whatever the things, because I have just telling some ghost things. Okay, don't mind for that, but just tell me what the questions are and answer, so that it will be more interactive to me and all of you. Okay, and whatever the doubt in the microgrid system, so ask me frequently. I just try to clarify all of your doubts, right? So here, just see the mathematical modeling of the PV system. So here, the basic mathematics I have used to design the PV system, and overall, I am just telling you all the systems I have designed on the PV means MATLAB Simulink, and it is tested in the Opelite laboratories, right? So parts of the and these equations are I have used by the use of the MATLAB Simulink system. Here IPB, the output current, I0, the reverse saturation current, ISC, the short circuit current. These are the parameter. K is the Boltzmann constant having the value of 1.38 into 10 to the power 23 to the power. So, and A is the compatibility ideal factors, and Q is the electron charge having the value of 1.60 into 10 to the power 19 coulomb. Then RSC, the PV cell containing parallel resistance. RSC is the series resistance. Now NS, you can say the number of series cells or PV cells or modules, right? So T is the temperature, B voltage, and B suffix T is the terminal voltage, VMP the maximum power voltage, IMP the maximum power current. These are the VOC, the open circuit voltage. And these are the parameters and I have taken to design the PV system. And these are the basic mathematics to use the design the PV system through the help of MATLAB and Simulink. And this means on the last one, this is the overall equations where I have connected, I have used NSCR. You can mark it as. So NSCR means number of series connected modules, and N parallel means NPR means number of parallel connected module. Whatever the how the this equation will be applicable, I'll just show you on the next line. Go for that also. See, these are the specification of the PV array. Where see, I have just telling you now how much PV cells are modules are used. So total PV module I have used here in the 96. And here the open circuit voltage is 64.2, and the short circuit current I have taken here 5.96, and the maximum power BMP, the maximum power I have taken as 54.7. I think there is a lot of PV modules. If you go through the PV means MATLAB Simulink, and you will go for the means lab view. So the lot of PV modules are available on inbuilt module. You can design that PV module, and you can also got some inbuilt model in the MATLAB Simulink in the lab view also. If you go for the Homer software also, Homer is used for the cost analysis. So lot of PV modules are basics models are available, and you can change according to your criteria and all the things. So there is no problem for that. But what my main concept is to know what I can design the PV module. If the PV module is not available, then you can design yourself by using the Simulink, by using the programming language. Okay. So these are the some parameters. That's why I'm just showing you what the parameters I have taken to design that PV modules. Okay. And here the maximum power of the PV cell is 305 watt, and temperature coefficient minus 176.6 MB per coulomb. And most important, though, how much modules are connected in series and parallel. So here I have mentioned, I have connected the 5 series modules having the parallel 66 modules are in the parallel connection. Okay, so irradiation level in the India, it is varies from 800 to 1000 watt per meter square. Okay, so here I have taken constant of 1000 meter per watt per meter square, but just a point of view. But when I have given you the simulation result, whatever the things I have designed and have derived from that, so you will see that I have varied that means irradiation level according to the criteria. Okay. Go for the next slide. So whatever the things I have telling you, this is the simple single diode model of the PV cell, and here the PV, the photovoltaic is connected to the boost converter. Okay, and here see the MPPT I have used, and the MPPT connection already given to the IGBT, right? So this connection, this MPPT from the D, it is connected to the IGBT switch. So it gives the pulses, right? And this pulses is used to trigger the IGBT switch, right? So I think all of you know the 5 types of triggering mode of the switch circuitries. One is the forward triggering, gate triggering, DV by DT triggering, light triggering, and the temperature triggering. Okay, I think all of you know that. So basically, in our industry, we are using the gate triggering methods. Okay, because it is easier, and the pulses are recorded to trigger the switches. If you remove the pulses, then switches is closed, and your connection is not harmed for that. But in the forward triggering, some amount of voltage we have to give, right? After that, means the junction will break down, then current will flow, and a lot of criteria will be available on the forward triggering. Okay, so here basically gate triggering we have used. Just remember that. And here maximum power point tracker. Right now we are using a lot of algorithms for the MPPT, and some artificial intelligence algorithm or optimization algorithms are available right now. One of my friend, he has worked in NIT Raulkela. He has worked in very good algorithm. I think this is 5 to 6 years ago. Gray wolf optimization. So here basic algorithms we are using the portable observer, incremental conduction method, constant voltage, constant current method, fractional short circuit current method. These are the basic algorithms we are using. So in the industry, basically portable and observer beyond method algorithms still now we are using. Okay, that's why I have taken this as the first primary reference. And here it is the PV and IV curve. You just look at that. In the PV and IV curve, you can see that when the voltage Vm and Im, this is the Vm Im means the maximum voltage and maximum current. At that time, the maximum power will generate. Okay. So just basic fundamental, just refresh for your mind. I have used that. I have just show you the MPPT, means overall idea. Here, in my
slide is not.
Slide is not moving.
Yes, sir. No, moving.
It is moving. Okay. Some low connectivity of bandwidth. That's why I think the slide is not moving. Sorry for that. Here, see the maximum power point tracker, right? So here I have comparison of both tracker. The left one is simple whatever observer tracker, and the right one is modified whatever and observer tracker. What is the basic difference between these two? I just am telling to you. See, on just lower one, del P is greater than 0. After that, if yes, then goes towards the condition del V is less than 0, and no, del V is less than 0. Okay. But here I have little modified that on the whatever and observer. Here I have taken the current level. on the middle part between the del P and del V. I have under that I have taken as the current also. Right. This is some changes, and I have given it as modifier potential. Why I have taken this? So basic region of the simple whatever observer. If you means irradiation level is not constant, right? All over there. I think all of you know. In the morning half it is lower. In the 11 it is little bit more, and in the 12 noon and 12 to 2 it is more peak. Then again it is decreases. So it is a parabolic curve. You can say that, right? So in the solar irradiation level, if we will go for the parabolic curve, so in the simple photographer and observer method, P and O method, what happens? It cannot track properly the irradiation level, right? So the maximum power, it cannot be tracked, right? So we cannot find out the local power and the global power. So this is some disturbances are coming. So can you unmute? Hello? Yeah, from some side, some disturbances are coming. Please unmute. Okay. So if the irradiation is changes, then the photographer cannot track the maximum power, right? So it cannot distinguish between the global power and local power. So this is the main disadvantages. What I have just telling you after the next slide. So just remember. So that limitation is covered by the modifier photographer observer. It is appropriately tracked when the irradiation level, also the power is increased. It is appropriately tracked. Why and how? I'll just show you. Let's see the on the below. I have given a table, right? See, when del V and del I is positive, means same sign, then the PV module understand that it is different irradiation level. Okay, if del V and del I have different sign, then PV module assumes that it is a constant irradiation. Okay, this thing makes the photographer and observer modified version is more reliable than the simple one. Okay. Here, whatever the thing previously I have described the DC to DC converter and DC converter. There are a lot of DC to DC converter there, buck boost, and buck converters, right? So overall, the description I have given you, and DC to AC converter, you just know as it is known as the inverter or voltage source inverter, you can say. Okay. So before going to the microgrid system, I have given some idea about how the grid integration is there, right? Grid integration means the most vital thing. You will design the microgrid system, but how the grid connectivity will be there? How you can connect the grid, right? This is the most vital thing. So microgrid system has the variable frequency, because solar and wind has the variable frequency, right? And grid has the stable frequency, 50 Hz, right? So how we will connect this microgrid to the grid? So we use two types of control: voltage source converter control, and another one is current source converter control. So current converter is basically not used; it is blocky, and practically the work in current source converter control is little bit difficult one, right? And it is so much a blocky one. So voltage. So basically, we are in industry factories. We are using the voltage source converter control. So here, I have given you some little bit idea about the voltage source converter control. Here you can see whole the structure on the part of below the PV array, inverter, and filter circuit. Whole the part is voltage control, right? So voltage source converter control is basically divided into two types, two parts: voltage control loop and a current control loop. What the things I am telling you. Here you can see that VDC and a BD reference, and these two signals are given to the DC link PI controller. This whole arrangement is known as the voltage control loop. And apart from that, all the things is covered in the dotted line, right? This is known as the current control loop. Okay, so I'll describe you. It is little bit complicated, I think so. And if you understand it, it is so much of easier. Just understand my point. What are the things I have described you? See, here I have taken BA, BB, BC, ROIB connection to the rotating axis to the direct and the quadrature axis. ABC to DQ converter. Okay. ABC to rotating axis ABC to DQ converter, right? So here also I have used the PLL. PLL means phase lock loop. The basic criteria or characteristics or working of the PLL is to create the phase angle. Okay, what is the phase angle? I'll just tell you. This phase angle is used to trigger or give the reference to the ABC2 and DQ converter. Okay, so here BA, BC, but you can take as BR, BY and RYB, BR, BY and BB, and also current IA, IB, IC to the, this three is given to the ABC to DQ converter, and ABC to DQ converter convert this two converter into the direct axis and a quadrature axis. Okay, and the phase angle is used to create the angle, and these angles are given to the, this phase angle is given to the ABC to DQ to trigger. Okay, then this ID and IQ is given to the a comparison circuit. Here you can see that, and from the voltage control loop, VDC and V reference signal is given to the DC link PI controller, and it is given to the ID. And this signal I have taken as this is ID star. It is my name. You can take another name. For the reference point of view, I have taken as the ID star. Right. This ID star is given to the comparator. Right. A block diagram will be set. This is the comparator. I have given to the comparator, and here from the current side, ID is given to the here. This is ID reference, and this ID is given to the another comparator, and this signal is given to the PI controller. Same thing has happened to here, DQ. Here, IQ has taken as 0. Why IQ is taken as 0? To make the power factor unit. But it is not practically possible. Ideally, you can take the power factor IQ is 0 means you can make the power factor unit. But practically, we cannot make the power factor unit. We can make it towards the closure, but not practically towards the 1. Okay, closer to the 1, you can say that. Okay, so here IQ has taken 0, and this IQ signal is given to the comparator, and this both signal is given to the PI controller. Okay, and this PI controller makes the two signals VD star and VQ star. Okay, and this VD star and VQ star is compared with the VD and VQ, whatever the converter, ABC DQ converter I have generated the VD and VQ, some purple line will be there. This two purple line is compared to this. Okay, and this two signal is given to the, again, reverse. First I have taken ROIB rotating frame to the direct and quadrature axis frame. Again, I have given the VD and VQ, right? Direct axis and quadrature axis reference frame to convert this to a rotating frame, ABC. And this ABC is generating the signal of UA, EB and AC signal. Okay, and this given to the pulse width modulation, PWM, right? The basic work of pulse width modulation is to give the pulses, right? Previously I have described you the gate triggering method is used to trigger the switches, right, by using the gate triggering method. Okay, so this signal is given to the PWM, and the PWM is used to trigger given the pulses, and this pulses is given to the IGBT switch by using the gate triggering method. Okay, so this is whole criteria of the BSCC controller to connect the microgrid to the grid and make the variable frequency and the constant frequencies to be the stabilized manner and connect this to the grid. Okay, so this is not the one method I am just telling you. Various methods are there. Means BSCC. So another 1 to 2 method I have show you the how the grid integration will be available. Okay. So go for the modeling of the BSU, the battery storage unit. You can say this is the mathematical modeling I have given you, and these are the specification. Whatever the specification I have used to model the BSU unit. Okay. This is the nominal voltage of 750 voltage, and the current is the 35.7 watts H. Okay, H means ampere hour. Okay, always remember the battery we can take the ampere hour. Okay, and the SOC level, state of charge, that is the 90%. Okay, so before going to the battery, I have given you we are using the not a single battery, we are the multiple batteries, and we will just take this as the battery management system. In the battery management system, we'll take the state of health, state of charge, temperature, these parameters basically we are using. Okay. This is the single diode model and previous circuit, whatever the describe I have previously. This is the controls, whatever the things I have designed and my team has designed to control the BSC unit. Okay. So see here, previously in the figure 1, the main figure I have given you the battery unit. So this is the battery unit having the buck boost converter. Okay, see here the buck boost converter, and the pulses are generated here. This is the control panel, control circuits, whatever and by using this control circuit, we are giving the pulses to the both switches. Okay, T1 and T2. You can see that VDC here, right? VDC is the voltage, DC link voltage, whatever the things I have described you. Just I have taken the first slide. Here, see, this is the VDC on the DC link voltage, which is connected to the voltage source inverter. This voltage I have taken. Okay, can all of you, can you see the first slide, whatever the slide, main slide I'm telling you? Hello? Hello? Yeah, all of you.
Sir,
okay.
It is maximum PowerPoint tracker slide.
Yeah. Okay. 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 Is this side is visible? BSU charging and discharging control?
No, not visible. Okay. It is stuck in maximum PowerPoint tracker.
Okay. Right now it is visible?
Yes, sir. BSU charging, right?
Okay, BSU
yes,
charging.
Sir.
Okay.
Yes, sir.
Yeah. Okay, why it is happened? I think my connectivity is very good, but why it is happening, I don't know. Okay. So here you can see that VDC, right? VDC is the DC link voltage, and VDC star I have taken as the reference voltage. Some reference voltage I have taken. Okay, and this this output I have given to this comparator, and this comparator output is given to the PI controller. Okay, the PI controller I have taken some KP and KI value, the tuning value I have taken. Okay, then it is generated the I battery star. I have just named it as, and I have taken the I battery voltage of that previous one, current, and given to the controller, and some limiter I have used. Within the limiter working is within this limit, the current will be there, and not below this and not beyond this. Okay, the limiter was only this much, and this is given to the pulse width modulation, and it is given to the AND circuit to 0 1 AND circuit. Basically the work is much 0 1 0 1, so it will give into the AND circuit. And here I have state of charge I have taken. If less than 0.9, then it is given to the AND circuit, and it will trigger some pulses will be given to that. So this is the basic simple control strategy I have used it for the BCU for charging and discharging purposes. Charging means when the state of charge is less than 90%, then not less than 90%, sorry for that, less than 20%, then it will taken as charging purposes, right? Then the buck boost converter act as the buck converter. Then when the load demand is more and the PV is unable to give the power supply, at that time battery discharges its power and given to the buck boost converter. At that time the buck boost is act as the boost converter and it gives the more DC voltage to the load and fulfill the load demand. Okay. Then the next slide, AU control schema, the auxiliary unit control schema. In the auxiliary unit control schema, just same concept I have taken. When the PV and the battery is unable to give the power supply, then at that time, this auxiliary unit come to the phase and fulfill the load demand. Okay, this is the control strategy. And here I have used the boost converter. Previously, I have used the buck boost converter, and here two IGBT or MOSFET switches are there, but here single switches is there. So we can see that. Okay. And here you can see the another one circuit diagram. Whatever the previously I have described you the voltage source converter control. Here another one voltage source converter control, and another one method for the grid integration and grid synchronization. Okay. So various methods, some changes we are in industry we are doing to make the power factor unit, to make the reactive power in controllable manner, right? So some changes we will doing, right? So, so this is another one circuit diagram, another way of connectivity for the voltage source control. Okay. So here, let some reference frame I have taken same concept, the PLL to make the phase angle and given to the ABC, so DQ means converter. And here I have in previously I have taken as IQ is 0. Here see I have taken as the BQ is 0, right? So small changes we are taking, right? And some comparator circuits are there, and by using some comparator circuit we are just giving compare and giving the voltage to the DQ to ABC converter again, and that pulses will given to the PWM, and the PWM is used to trigger that inverter. Okay. This is the whole arrangement, whatever the things I have telling you right now. This is the arrangement for the things I have told here. This is the things I have written here. You can take the reference. Okay. And this is the supervisory control schema. So for the working principle of this supervisory control schema means you can say that whole control strategy of microgrid system and grid system means this is the you can administrator control, right? From here you can control whole the system. Okay. So let's tell about that, describe what the supervisor control strategy is there, what the things I have taken as. Here BDC means DC reference voltage, DC voltage means actual voltage is less than the reference voltage. Then it is BSU discharge means the BSU power is more and BSU discharge that power. And if condition is no, if condition is yes, then it goes towards the SOC level. Means previously I have described you SOC means state of charge. The state of charge basically in the industry practice we are using between the 90 to 20%, 90 to 20%. Below it is harm and above it is also harm. So always the good battery health is in between 90 to 20%. Okay. So that's why I have taken as 90 to 0.9 to 0.2. Okay. So it checks the SOC level. If the SOC level is yes, is less than 0.9, then it is supply the power to the load L1 and L2. What the L1 and L2? I'll just apply it. L1 is the primary load or constant load. L2 is the variable load. Here I have taken the two types of load. Why I have described you on the next slides. But remember that two types of load we are taking. If the condition is no, then it checks the SOC level is between 0.9 to 0.2. In between that, yes, then it is again supplied to the both type of load. If condition satisfied no, then it is checks PV power is less than the load power. Then the auxiliary unit come to the phase to supply that power. Okay, so this is all about the control strategy, and some conditions here I have written. If PV power is greater than the load power, then PV fulfills the load demand. If the PV and the battery power is less than the load, then L2 is disconnected, means the load, low priority load, we can say disconnected, and L1 is supplied to the load. And if SOC level is 0.2, then auxiliary unit is come to the phase to supply the load. Okay. And here, I think all of you have known about the STATCOM circuits, right? Fact devices, right? So there are a lot of STATCOM devices, DSTATCOM, EPQC, Unified Power Quality Condenser, EPQC, PFC, right? So here I have used the DVR as a simple circuit, and it is little bit blocky, you can say, but simpler than the STATCOM devices, EPQC, and Unified Power Quality Condenser, and DSTATCOM. Okay. So it is blocky and less costly than the STATCOM devices. It is so I have used the DVR. You can use the STATCOM devices, no problem. The basic work of this DVR and the STATCOM devices to compensate the voltage, right? Sag, swell, the fault conditions, all the things are happened, right? So you can compensate the voltages. So here, this is the basic circuit diagram of the DVR. In the DVR, you can say I have taken as a energy storage, okay, and a DC link capacitor, and here voltage source inverters are I have used, and some LC filter is used. LC filter basically used to reduce the current and the voltage harmonics, okay, and injection transformers also there, okay. So in the injection transformer, it is connected in series with the grid. When the fault, sag, swell are happened, then it compensate that voltages. Okay. And here the controller, PI controller is used to trigger the voltage source inverter. Here I have used here the PI controller, and this is the basic circuit diagram of the PI controller. And here I have used some PI means load voltage, means this load voltage I have converted into the rotating axis to direct and quadrature axis, and the PLL previously I have described you to make the phase angle to, and that phase angle is used for the ABC DQ converter. And this BD bit and BQ is compared with some reference BD and BQ. And this is given to the PID, some controller here, discrete PI controller I have taken, integral control and the derivative controller. And this controller is used to give a signal which converted into the DQ to ABC, again the reference frame, the direct and the quadrature axis to the ABC frame, rotating axis frame. And this ABC frame is given to the pulse width modulation, and pulse width modulation gives the pulses, and this pulses is given to the voltage source inverter to trigger the AC voltage, right? So here I have used the energy storage. This energy storage is given, always knows the DC voltage, and the DC voltage is given to the inverter, and the inverter IGBT switches are used basically by using the pulse width pulses, and it work on 180, 120 conduction mode or something conduction mode we are just working, and it generate the AC. Right now the multi-level inverters are coming into the phase. Whatever the to make some voltages, means sinusoidal voltages. Okay. So this is all about the DVR. And whatever the mathematics, VD, VQ, V0, I think these are the basic mathematics I have used here. and the comparison will be there. Whatever in the figure I have described you. Okay. So by using this, I have designed the DVR and I have connected this DVR into the grid in the series connection. And this DVR is used to compensate the voltage when the fault factual arises. Okay. To maintain the power quality in good manner, to maintain the TSG less than 5%. Okay. This is overall the simulation results and discussion. Whatever the previously I have described you, this whole arrangement we are doing and all the things we are doing means designed. So these are the simulation results. See, figure A, this is the irradiation level. See, the irradiation level is not in the morning hour it is low, and the evening hour it is less, and it will be increased, right? On the noon it is 12 to 2 it is more, and again it is decreases, right? This is the irradiation level of PV. Okay. And I have already told you here I have used the modifier portable observer method. Okay. Here you can understand the how portable observer and the modified portable observer works, right? So here what happened in the see how accurately the modifier portable observer tracks the PV power, right? If the means irradiation increases, then PV power increases. If the irradiation decreases, then PV power increases. But in the simple portable and observer method, if the irradiation increases, it cannot find the global and local maximum power. Somewhat it will be rotate means stick means and thus whatever observer understand that okay it is the power maximum power, but it cannot understand the irradiation level is increases. I have to increase that certain amount. I have to increase that power, but it cannot understand the simple one. Okay. So you can see that how accurately track the modified portable observer track that. Okay. So here, two types of load I have described you, L1 and L2. In the L1, the fixed load is there, the most primary load and the most important load. Okay, and L2, the variable load. This is not the primary load. This is secondary load. If it load is disconnected, it is not harmful. So that's why I have taken as primary and means secondary load. Okay, once L1 the primary one, the most important one. L2 is the not so much of important. Okay. Come to the SOC level. See, here in this figure, this is the state of charge. Already I have described you. The state of charge is varies from 90 to 20%. Okay. See, here some previously here. See, in the figure A, the SOC level, the irradiation level is 0 from 0 to 1 per second. Means on the morning hour it is 0. And see, from 90 to 89.98 it is drastically reduced because of the irradiation level. The irradiation power is 0. The PV power is 0. Right, 0 between the 0 to 1.4. The irradiation is drastically reduced, and this is rapidly reduced because my condition says that when the PV power is unavailable, the battery will give the demand or fulfill the demand, right? And see here, at this point, the irradiation increases, and see here, from around 1.4 second to 2 second, the irradiation increases and the power also increases. And see, within this time period, okay, some the drastic manner of SOC charge is not decreased. It is inclined somewhat. Okay, so it is not decreased, and it happens till 2 to around 8.2, 8.3 seconds. Okay, it happens because the power is in good manner. Okay. Again, see, the power is decreases to 0. Again, see, the SOC level is decreases in drastic manner. Okay. So my control circuit is works very good here. Okay, you can understand that point also. if anyone has some doubt in this two figure A, B, C, and the D figure, please ask me. Is there any doubt, or is there any conceptually wrong? Means if you have any cannot understand, then you can ask me. Okay. Here, see, this is the another one point. The battery state means power. See, the state of charge of battery, the figure B, the middle part of the PV power, okay, and the figure E. See, figure B and a figure E. This is replica, means reverse, right? The PV power is increases, the battery power is decreases, the PV power is 0, then the battery power is 0. See here, when the PV power on the first half is 0, then battery gives up power. When the PV power is more, then battery goes toward the 0. When the PV power is again decreases, then battery suddenly peak to the means more, and it gives the fulfill the load demand. Okay, how in this manner our control manner, our supervisor control strategy is worked, whatever the I have described you. Okay, and this is the auxiliary unit, and basically it is 0. Why? Because of when the state of charge is 0.2 of battery or less, and when the PB and both battery are unable to supply or unable to figure out the load demand, then at that time auxiliary unit come into the phase. Okay, and this is the DC link voltage. Okay, the DC link voltage is maintained constant. So here ideally it is constant, but practically it is not constant. Always I am telling to you, so it is ideally constant. Okay, not practically, so it is somewhat varying. Okay, and these are the simulation result. Whatever the dBr already I have told you previously, right? So this is the voltage of dBr. See, understand my point. Whatever the dBr I have described you, and the faults I have taken here. See, here supply voltage at F1 means fault. So here LLG fault will be there, right? So in the LLG fault, this is the severe fault. See on the left hand side figure, the whole within this time period when the fault is occur, the supply is 0. Here dBr inject that power, and the right hand most right hand figure, see the compensated voltage. Okay, and come to the second one. Here LLG fault is there. In the LLG fault, both line goes towards the 0, and one line is supply is there, and the dBr see compensate their power, and this LLG sorry dBr middle figure that compensate means cannot compensate, they inject the power, and the most right hand side figure it was compensated. Okay, and see figure 27, sorry, slide number 27, and in this figure LG figure is there. In the LG figure, see how the district connection is there, and the middle portion inject the power of dBr by the injection transformer, and the LG is compensated. Okay, the final figure right hand side figure is compensated. Okay, and also in the LL figure same thing happened. So I have given you the different conditions, and the triple L fault also see this same thing is happened. So different scenarios also I have told you that this fault are happened many times in the grid, and our DBR system is most capable and most efficient to compensate that fault. Okay, and make the voltage level good. Okay, so that our power quality also good. Up to this, anyone have any doubt? Hello? Hello? Hello, am I audible?
Yes, sir, you are audible.
Any doubt? Any doubt here? Up to this, I have told you most means a lot of things in the DVR, how the PV battery auxiliary unit connectivity will be there. I also show you the two types of grid connection, right? In the one connection IQ is 0, in one connection VQ is 0. All the things, most of the things I have told you. Any under the control strategy and the simulation result, what the PV tracking system will be there, how the PV and the battery functions, right? So any doubt, so you can ask me. Okay, then no, then go for the hydrogen energy. So right now in India, we are working on hydrogen basically. The hydrogen is the green energy, you can say. So basically, we are working on green hydrogen. Also, in some areas, blue hydrogen also there. Blue hydrogen means you can say that the methanol, we can use the methanol, that is the blue hydrogen. And if you take the water, then that is the green hydrogen. Okay. So here, see, I have taken the green hydrogen. So in this main figure, I have removed the auxiliary unit. So no need of the auxiliary unit. I will use the hydrogen energy. Sorry, sir. I have so I have used the hydrogen energy right now. So here, see, on the end of the figure, I have used the solid oxide fuel cell. In the solid oxide fuel cell, I have used solid oxide fuel cell. There are a lot of fuel cells are there: proton exchange membrane fuel cell, alkaline fuel cell, solid oxide fuel cell. Okay, so a lot of fuel cells are there. So why I am using the solid oxide fuels in short term SOFC? Because of its efficiency is good. That's why I have used that fuel cell. So around its efficiency is now 65% efficiency it has having. I think I can't remember that, but it is around 60 to 65%. And in the proton exchange membrane fuel cell, it is around 40 to 50%. Okay, alkaline is all less. Okay, so we are using the more solid oxide fuel cell right now because of its efficiency. And see, in the solid oxide fuel cell, I have used the boost converter and here I have used the electrolyzer. The function of electrolyzer is to divide the water into the hydrogen and the oxygen, right? So hello. Hello. Yeah, some disturbances are coming. Can you unmute? Hello. Electrolyzer. Hello.
Sir, please mute.
Mute. I can. Okay. Here electrolyzer is there. In the electrolyzer, we are using the taking the water, and water is divided into two types. Water is divided into two elements: hydrogen and oxygen, right? So here, this hydrogen is used as a fuel to the solid oxide fuel cell. Okay. So always remember, when we are using the hydrogen, then this water then as a basic element will take as the green hydrogen. Okay. So this water is divided into the two elements of hydrogen and oxygen, and H2 is used to store in the tank. Also, in some cases, oxygen also stored, and in some cases, oxygen will inject to the atmosphere, right? So most of the companies right now taking the hydrogen and oxygen in different storage tank and they make them stored. Okay. I think all of you know about the corona, and the corona time, the oxygen is so much of necessary things, right? So to store the oxygen is very much a vital one. So here, storage tank stores the hydrogen energy, and this hydrogen energy acts as a fuel of the fuel cell. Okay. And in the electrolyzer, see, across the buck converters are used. Okay, to trigger the electrolyzer, buck converter is used. I have very low amount, so I have used the buck converter. Okay. So here the overall modeling of the electrolyzer and the circuits of the electrolyzer. What the circuits I have used, okay, in the electrolyzer to model the electrolyzer. Okay. So I'll go for the little bit faster, and the time is around half an hour. So I have to conclude. Most of the slides are there till now. So, and this is the simulation model and a mathematical equation of the storage time. Okay. And this is the fuel cell and mathematical equation of the fuel cell. Previously, I've told you H2 is divided, H2O is divided into the hydrogen and oxygen. So you can see that H2 plus half of O2 is the H2O plus electrolyzer and a generator heat. Okay. Here, solid oxide fuel cell. This is the basic element: CB, conversion factor, nominal voltage, nearest immediate voltage, Faraday's constant. These are the basic constants and basic equations, terminologies I have taken to design my solid oxide fuel cell. And these are the basic parameters, specifications and values I have used to take in the solid oxide fuel cell. Also, if you go for the MATLAB Simulink, I think I have right now I am using 2019 polyphase B circuit. That is my authentic version. I have taken using, and right now 2025 will be there. So I think in 09 the advanced polyphase circuit, so polyphase version also released, and you can see that and go for the Simulink model, and you will find out lot of SOFC model, lot of fuel cell model you can take. You can take various model. Here I have used 5 kilowatt SOFC. Okay, these are the parameters for the 5 kilowatt to design the 5 kilowatt SOFC model. Okay, and these are the basic mathematics where I have used to design the model of SOFC through the MATLAB simulink. Okay, and these are the basic whatever the things I have described you previously, the control strategy. Okay, in the control strategy, and this is the another one control strategy for charging and discharging the battery storage unit. And this is the control strategy of SOFC. Okay, so here in the SOFC, I'm just telling you for the control strategy I have used. You can see I backed boost, right? You have a boost means here the meaning of the I backed boost, the output power or output current of the battery. Okay, and this battery output current and IDC. IDC means the DC link current is compared and given to the PI controller, and some reference current will be taken out, and this reference current is compared with the fuel cell current. See, IFC current, and this is the IFC current, and this is the reference current. This is compared, and limiter is there, and within this limiter output is given to the pulse width modulation, and it is compared with the SOC charge. Here I have taken 30%. Okay, because of why I have taken a 30%, because of I just check that means I just want to more utilization of SOFC level rather than battery. That's if the 30% means state of charge is less than 30% or equal to 30%, then the battery what the things solid oxide fuel cell is come to the phase and fulfill the load demand. Okay, that one motive I have. So I have to means use SOFC more and more. Okay, then this is the SOFC level I have used, and this SOFC level is given to the comparator, and the pulses are generated, and it is used to trigger the boost converter of T1, and this T1 is used to trigger the means boost of the voltage of SOFC. And this is the electrolyzer comparison circuit. This is the electrolyzer comparison circuit. In the electrolyzer comparison circuit, again, same one of control strategy I have used here. I battery boost I have used, that is the battery voltage, battery output DC boost converter voltage, again IDC converter, then electrolyzer comparator is there. Then here some changes I have given. See, here I have taken IFC current, right? IFC current is the output current of the solid oxide fuel cell. Okay. Here I have taken the I electrolyzer, means the I electrolyzer current of the electrolyzer current. Okay. Then some changes I have taken for the controller and given to the gate pulse to the buck converter. Okay, buck converter, it main work is it is make the more DC voltage to the low DC voltage. Because why I am using the buck converter? Because electrolyzer work on very low voltage. Okay, that's why I have used the buck converter. This is control schema. Okay, this is another one control schema I have used. I think I have not added that figure. Okay. Then here, this is the supervisor control strategy. Previously, I have given you the one model that is consists of PV, battery, auxiliary unit, and here I have used the another one model, PV, battery, and the fuel cell. So I have used one control strategy, sorry, supervisor control schema, and this is the another one supervisor control strategy. See here, the control strategy. Here, some modified control strategy also I have given. Here, it checks the PV power is greater than the load power. If condition is yes, then PV power check state of charge. State of charge belongs to the battery. If state of charge is greater than 90% or less than 90%, sorry, less than 90%, yes, condition satisfied, then go to the storage, then check the storage tank. If the storage tank is full, storage tank means where the hydrogen stores. If the storage tank is full, then it does not inject the power to the storage tank. If no, then it inject the power to the electrolyzer, then it fulfill the storage tank. Okay. If the condition PV power is greater than load power, condition is not satisfied, means the condition is no, then SOC again check. If SOC level is greater than equal to 90%, okay, yes, then it goes to the battery to supply the power. No, then again it is checked, the SOC level is greater than 40%, yes, then it is again battery is supplied to the power if the PV demand is low. Always remember here, when the PV demand or PV power is low and the load demand is low, then this control strategy works. Okay. If no, then the more extra amount of PV power is given to the electrolyzer and the battery. Okay. If condition is no, then it checks the solid oxide fuel SOC charge, state of charge is greater than 30% or less than 30% if the condition is satisfied, or no. If yes, then battery will supply the power. If no, then battery is supply the yes, then electrolyzer battery does not take the power and it gives the power to the electrolyzer. So this is all about the arrangement and the things, and this is the theory. You can I will share that PPT to the Prashantini and you can check that what the conditions I have means developed in this algorithm. Okay. And this is the simulation result and a discussion of the what are the things. And before as the figure, previous simulation and result I have explained, this is same. The irradiation level and the PV power and the two types of load. Changes happen here. State of charge. Here I have taken as state of charge greater than 90% and less than 30%. Okay. And this is the battery power. You can see that. And when the battery power is more than 90%, then power of SOC is no more. Okay, less. Here previously I have described the condition What when the battery power is between more than 90% or between 90 to 30% between, then SOFC does not trigger its power to the load. Okay, but when the its voltage is given but power is zero, when and this is the hydrogen energy generation, and this is the hydrogen P electrolyzer power, and this hydrogen energy is generated when the PV power is more, and it supply the to the electrolyzer, and electrolyzer divide the water and water into the hydrogen and oxygen, and this is the hydrogen generation, and this hydrogen generation is stored in the storage tank. This is the DC bus voltage. Always I am telling you, DC bus voltage is practically not constant. It is little bit vary. And listen here, uncle. This thing. Previous the simulation models I have described you, its state of charge is more than 90% or between 90 to 30 or 25%. When the state of charge is less than 30% or it is 25%, see, the SOC level decreases rapidly. At that time, battery also not fulfilling the required amount of demand. And you can see the PSOC level is in the formation manner. Okay, just a minute. सब साफ सफाई कर दीजिएगा. ओके, और 4 रोटी बना दीजिएगा. Hello. Here PSOC or SOC come into the phase. Why? Because state of charge is less than 30%. Okay. And this is the voltage and the current waveform of the hybrid renewable generation system. Right? What the voltage and the current will there. See here, the voltage and the waveform of the current for the duration of the 0 to 10, and I have got a small portion between 7.9 to the 8.1, and you can see how the voltage voltage RYB or ABC you can say is there. Okay, and this is the THD analysis, and you can see that the THD level is 0.17. Okay, this is very much good, means my voltage and the current quality is very good, and the voltage quality is very good. This all about the simulation result of the current. You can see that current harmonics is less and the THD level is very good. Okay, and this is the load voltage waveform of the nonlinear load. This is the load voltage and voltage and the current, and this is the THD level, and this is the current voltage and the current, and this is the THD level. Okay, here power waveform of the nonlinear load. Nonlinear load already I have described you. Somewhat it will be more and somewhat it will be less. It is the variable load. I think I already show you, and this is the nonlinear load also. Or waveform, and the voltage waveform of the variable load here, and this is the THD analysis. I think you have already described with the L1 and L2. So these are the basic waveforms I got, and THD analysis I have done here. This is the nonlinear load of variable load. Some portion it will be the power when the load is 0, then it will be 0, then current will be somewhere the power will be load will be there, then current will be there. When the 0, then 0. So this is all over the structure. Okay, and here the subplot of the current waveform from some time period to some time period I have taken, and this is the THD analysis, and THD is 1.0, somewhere it is a little bit more. Okay, and this is the power waveform of the variable load. So all over the conclusion, I have told you this is the load of HRGS, this is the load of the constant load and the variable load. Whatever the things I have told you under the THD analysis I have done, all the things I have done, and this is all over the conclusion. Whatever things I have described you in the model of that HRGS. Okay, so I have described the two types of model. One is the PB BSU battery storage unit and the auxiliary unit, and one is the PB BSU and the hydrogen energy. Here I have removed the auxiliary unit. I have used the hydrogen circuit. So you can see the two figure, and here a basic work I have done under the cost analysis, right? For the cost analysis, you can design the model, you can design the control circuit, you can design whatever the things you have designed in the R&D. Okay, no problem for that. But if the cost is more, if the system is not feasible, that is wasteful, right? In the industry point of view, I am telling to you. So here the most important thing is whatever the things you have designed, whatever the system you have designed, the lastly the cost will be the is most vital thing for the designing. Whatever the cost for the designing the model, and what are the output of the means cost, and what are the maintenance of the cost, and what the benefit is given to the by the model, all are analyzed. Okay, so here two types of models I have told you. Two types of model I have given you. First one is the PV battery and auxiliary unit. Here auxiliary unit I have given replaced by the auxiliary unit with the diesel generator. GN50, you can say this is the diesel generator. And right hand side figure I have told you the PV battery and the fuel cell. Okay. So these are the two model I have used. These two model designed in the homework to calculate the cost analysis. This is the table content and specifications of model 1 and model 2. Model 1, the left one, and the right one is the model 2. And these are the specifications I have taken to design that model in the homework software. Okay. So I have a question to all of the listeners. Have you known idea about homework software? Anyone have? Hello, am I audible?
Yes, sir. Yes,
Yeah.
sir.
Anyone have you know about the homework software or any other cost analysis software? No problem. Whatever thing. Any other cost analysis software? Have you known? No. Okay. Just practice that. It is free of cost for 28 days. After that, you have to pay them, and you can analyze. And this is the real-time software. You can say that every area you can take any area. If you come for the Odisha Bhubaneswar, if you come to the Odisha Bhubaneswar, then you will go for the some area of the Bhubaneswar, and you can virtually set up your plant, and you can take the irradiation level of PV and the wind generation also. You can take that and you can analyze that area, how your system is feasible. All the things you can do with the homework software. And a lot of cost analysis software is also there, but basically I've used the homework software and MATLAB. Okay. See, this is the here I have designed a area in Amaravati. One of my student, she has on fourth in this state, she has her defense and she has done that work in the Amaravati area. This work conducted by her and me also. So this is the generator power output, and this is the inverter rectifier output, and the battery storage lithium ion. I have used the battery. This is the output of the lithium ion battery. This is the hydrogen storage tank output over the whole year. Okay, don't be confusion. I have taken out the whole year.
Sorry, sir. Hello.
Uh-huh.
Sir, the slide is in supervisory control scheme of HRGC, or it has changed?
Okay, no one has just told me. Okay, have it is same.
Hello. Hello. Hello.
I think sir has offline. Ma'am, wait.
Am I audible?
Yes,
Yes, sir.
Yes, sir, audible.
Just tell me. Yeah. Yeah, just tell me because I don't know. My connectivity is more very good, right? So why thing has happened, I don't know. But they just told me that I have taken 2 to 3 slides more.
So
That's why.
now this is
Okay, no
HRGC
problem.
homework.
HRGC homework. I have explained for the 6 to 7 minutes about this. Okay.
Okay, sir.
Okay.
Actually, it was not Sinha.
Just tell me. The when you cannot see na the stock some slide will be stock. Just tell me so that I can again means come to previously and replace this. Okay. And this is the specification of model 1 and model 2. What the specifications I have taken to design that model, and this is the HRGS system, and this is the HRGS homework inverter and a rectifier output, and a hydrogen storage tank output. Okay. Here, HRGS homework software, the whole power from January to February. The system I have taken PV, generator and battery. This is the left hand side is the whole means you can say the bar graph of their generation capacity, and here I have given you the monthly generation capacity. Okay. Then here PV power generation for the module 1, PV power generation of the module 2. Then here battery backup generation of the module 1 and a backup generation of the module 2. You can see module 2 is more better than the module 1. Okay? Module 2 I have used the green hydrogen or fuel cell, and the module 1 I have used the diesel generator. See, 292 plus improvement will be there in the module 2, right? Then here, grid purchase rate is more rather than the module 2, right? So in the module 1, we have purchase from the grid. In the module 2, purchase is less. And here, the table analysis is most important. Why? I think all of you read about the ESG, environmental social governance. Right now, if you go for the green energy, wind, solar, hydrogen, then environmental social governance things is vital in terms of carbon emission, in terms of nitrogen oxide, NO2, CO2, all the emissions. These are the most important one. So here you can see that model 1 net present cost is 21.42 million and a model 2 cost is little bit less. See 16.86. So my model 2 is efficient. The fuel cost is 3.61 million. Here the fuel cost is 0 because of water. We are taking the water, right? Water cost is 0. The grid energy cost is 2.43. Here the grid energy cost is 0.41 million. 41 million. Okay. So these are the comparison between the model 1 and a model 2, whatever the thing I have designed, and this is the cost per unit of electricity. See, in the model 1, 7.65 rupees per megawatt kilowatt hour. Here see 6.15 rupees kilowatt hour. See, means cost of charges, it is less in model 2. So my model 2 is more efficient than the model 1. And this is the CO2 emission, SO2 emission, sulfuric oxide emission, CO2 oxygen, NO2 oxygen, nitrogen oxide emission by using the module 1 and the module 2. See, my module 2 is most better than the module 1. See, in terms of minus 80%, minus 70%, minus 100%, minus 60%, so reduction is so much of less, CO2, SO2, NO2. So this is known as the environmental social governance. So my green hydrogen is more efficient. कल नहीं आऊंगा, कल आप मत रहिए, कल और परसों में घर में नहीं रहूंगा. Just a minute, everybody. कल और परसों मैं नहीं रहूंगा, तो मत आएगा. 5 तारीख को आएगा, कल और परसों 5 तारीख में कॉल कर लूंगा. Hello. So here the environmental social governance works, right? So most of the scenario cases, government is concerned about the ESG right now. So we are moving towards the green energy. We are moving towards the lot of solar plant, floating solar plant, wind plant, onshore, offshore. We are just using because of this, because to reduce the carbon emissions. Okay. So my main motive to show this all of the things is how my model performance will be the good, how the model cost will be the less, how the model carbon emission will be less, how the model is efficient is more. That's why I have given you the two types of model. I have done their cost analysis and I show you my model 2 where the hydrogen energy is there. It is working so much of beautiful manner, so much of good manner than the model 1 where the diesel generator is worked. Okay. This is the overall comparison summary of cost summary. You can see the cost of model 1 and model 2 for the 10 year, 15 year, 20 year and 25 years. How the cost will be there, including from maintenance cost, all the cost. Okay. So from these two figures, we can see that model 2 is more efficient, more reliable than the model 1. Okay. Overall, all of you, I have concluded all of my work here. I have shown you the two types of model. I have shown you the StatCom, DVR, all the things. I have told you the cost analysis. Okay, this is all about the work we are currently doing. Our industry practice is there. Okay. And you can follow me in my Google Scholar profile, my GitHub profile, whatever the means machine learning algorithms we are doing, Tableau. Okay, and my LinkedIn profile also. Okay. So this is all about my work, whatever the I have doing on modeling simulation in the green energy field, hydrogen energy field. Okay. So anyone have any question, you can ask me. I can clarify all the doubts. Am I audible?
Yes, sir, audible.
Okay. If anyone participant has any doubt, just ask me. Any modeling, homework, software.
Dear
Just tell
participant,
me.
if you have any doubts, then sir is here. Then you clarify your doubt.
Sir, is in any criteria to choose the MPPT? Which type of MPPT is suitable for system?
Okay. Very good question. I just expect that type of questions. Not criteria we have telling. We have most of the research are going on, right? We are using the AI models. We are using the optimization algorithms. We are using the modifier algorithms. So basically, in industry practice, currently we are right now doing whatever observer and modified whatever observer methods. And you can tell that some AI algorithms we are using, but till now in India we are not implemented. Okay, in some foreign countries, you will go for the Denmark, you will go for the UK, USA. Basically, in the Denmark, a lot of work are going on in this scenario. Okay, so criteria you cannot say that, but our criteria you can say that how efficiently your irradiation level is tracked. Whatever the thing I have shown you now, if irradiation increases, increases, right? How efficiently your algorithm, your MPPT algorithm will track your power, irradiation level, and the power is increases. Okay, this is the basic criteria. Nothing but criteria. Okay. Any other?
Yes, sir. Yes, sir. Thank you, sir.
Welcome.
Good evening, sir. Good evening, sir.
Good evening, Monalisha.
Good evening, sir. It was a very nice presentation. Sir, actually, I have two questions. First thing is that what other controllers can be implemented in this system? And if the time permits, can you please elaborate more on hydrogen technology on which you are working right now?
Okay. Controller means which type of controller? I have used a lot of controllers I have. So which type of controller you want to ask?
Recently, sir, the more research works are going on artificial neural network and machine learning. So can these be implemented?
Okay. Yeah, you can implement. Okay, I will just tell you that is my favorite area. Prashantini also told me that to tell about this AI control systems. Okay, so basically, whatever the things I have got here, we are using machine learning, deep learning methodologies here. So in the machine learning, AI is a very vital thing or big thing. Optimization techniques you can take the particular one, the basic optimization, gray wolf, cuckoo search. You can show the well optimization, advanced well optimization. Right now, I have taken a research article right now in the previously. A advanced optimization algorithm also means gray wolf, some modified gray wolf optimization algorithm also available. Some vectorized form gray wolf right now in 2025, and a Varus optimization algorithm also they are available. So a lot of optimization algorithm and mathematical algorithms are so there. This is the AI algorithm. Apart from that, we are using the machine learning models. The machine learning models, you can say the linear regression, multiple linear regression, descent tree, random forest, support vector machine, descent tree, then XGBoost, AdaBoost. Lot of artificial algorithms we can use, and we can optimize that algorithm. We can use that algorithm in these models to track or to improvise our means control strategy, right? So these are the machine learning algorithm. You can read that the machine learning algorithms in the form of you can take the data sets, whatever the generation data sets you can take, you can along that data sets into the algorithms into the 70-30% or 80-20%. Apart from that, they have the score of accuracy score in terms of R square value, adjusted R value. Then apart from that, you can take that. Okay. So this is a huge class. I cannot within the short time period I cannot explain, but just I will explain you the linear regression and multiple regression. Just simple one. I think linear regression, if you know about that, the straight line equation, that is y equal to mx plus c. I think all of you know that. So here y is the independent variable. I'm wrong. Y is the dependent variable and x is the independent variable. So by using these two variables, we learn the algorithms of linear regression, and we divide the data set into the 70-30 or 80-20, not beyond that. Okay, this then we can learn and we can find out the accuracy level. Okay, so in this manner we can design that. So we'll go for the a lot of algorithms are there. Support vector machine right now, very good algorithm. One of my friend Devani Mishra, I think Mona Lisa, you know him. He is the professor in IIT Bhuyan. He has worked in support vector machine. Very good work he has done in the support vector machine. Also, random forest will be there. Advanced algorithm, XGBoost, AdaBoost, also there. The advanced algorithm right now. 2 to 3 algorithms are there. CatBoost also there. I've just read that some paper of IEEE transaction paper. The CatBoost also there. Some recent algorithm. Then Light GPM also advanced technology also there. You can use all these algorithms to control the methodology and all the things. Okay.
Okay, sir.
Any others?
Sir, I think you left another question to throw some light on hydrogen technology.
Okay, hydrogen technology. So in India, we are right now working on green hydrogen, but and the blue hydrogen right now coming to the market in India. In the blue hydrogen, you can use the methanol, CH4, the composition. Okay, so in the CH4 blue hydrogen, we extract the hydrogen of H4 and carbon CO2. Okay, so green hydrogen right now NTPC has developed lot of work in the green hydrogen area. Also on INA, the renewable, also they have installed the green hydrogen. I think so. I can't remember the not INA. Sorry. My mistake. The Samcrop, the company, that is the foreign company, it has established the green hydrogen plant with the help of NTPC. I can't remember some MOU is there. I can't remember some. It has also established the green hydrogen technology with hybridization with the wind energy. right? So whatever the thing I am telling you, na, the extra amount of the wind energy or extra amount of the solar power is given to the hydrogen or electrolyzer, and the electrolyzer divides the water into the hydrogen and oxygen, and this hydrogen is stored in the storage tank, and the oxygen either it goes to the atmosphere, otherwise from organization it also stores that, and they sells that O2 to the medicals also, right? So Semcrop, which the company NTPC also the company, they are working on the green hydrogen also, and right now I am till now I am not forecasting the green hydrogen, but some AMU will be signed by us and some generators. We are the QC company. Regarding the green hydrogen, hopeful within the 1 year that we are also capable to forecasting and scheduling for the green hydrogen also. Okay, so you can work on the green or blue hydrogen, and this is the vital thing area regarding that. And I got a call and offer from Denmark from the green hydrogen. They are working in very good manner. If you go for the LinkedIn profile, if you go for the LinkedIn, I have reposted that to Denmark and USA, UK, their green hydrogen, they are working on that, and you can follow that hydrogen energy. You can find a lot of articles and a lot of research articles, lot of work in the practical scenario in the green hydrogen. And India, it is working. When I have started my work in 2014, then I have worked on the hydrogen. So lot of not improvement is there in the hydrogen energy. Till now, at that time, the practical only the R&D section are working on that. Right now, most of the companies are interested on the hydrogen energy. If you can make the career, you can go for that hydrogen energy also, no problem. And read the hydrogen and some Fathabadi paper, I can't remember that paper of Fathabadi, some hydrogen energy that is published in hydrogen energy. That Fathabadi is worked very good in the hydrogen energy. He has worked very good manner. And a lot of papers in Fathabadi, the name of his, and I think he's from Denmark, I think. Denmark, he's from Denmark. He has done a lot of very good work in hydrogen. You can read that. Also, I have taken some reference of his paper on my paper also. You can go for that. And the finally, I think the green hydrogen energy is vital area right now. A lot of research are working going on, and a lot of industries are working on that also in India, and a lot of AMU scientists also there. So government also initiatively taken on hydrogen energy. Okay. Any other?
Hello, sir.
Yeah. Yeah.
Sir, in your cost benefits analysis, have you included the carbon credits?
Carbon credit. Good question. Here in the Homer, there is a inbuilt you can say that inbuilt ESG model will be there. Environmental social governance model will be there, and in that model you can find out the carbon credit and CO2 then SO2 model. You can find out that ESG model. If you have the authentic version, you have you have the authentic version of Homer software, then you can find out that ESG model. Means I think in 2019 onwards, Homer software has added 19 or 20. I can't remember that, but it has added the CO2 model. ESG model, environmental social governance model. You will go there and you can add the CO2, NO2, whatever the emission level you can add. It will show that, and it will calculate on practical basis. Means some area you have taken, and in this area, in that area you have taken that means radiation level, wind speed, and the emission level. And I had this Homer software takes the data of NASA, right? So it take the data of NASA. According to the data, it calculate the CO2 NO2 level. Okay, you can take that, and you can purchase for that. I think I am not the crack version. If able, then I can provide that, but I will also purchase for the research. Okay, or any other?
Thank you, sir.
Welcome.
No, sir.
Any other? Please ask.
Okay, I think, sir, there is no doubt from participant side.
Okay, thank you.
Thank you, sir. Thank you, sir. So, thank you so much, sir, for such a comprehensive
Welcome.
and engaging talk. I truly appreciate your time and expertise. Okay.
Okay, thank you very
And,
much. Thank you, everybody.
sir, and this gives us a clear perspective in today's world. On the behalf of organizers and all the participants, I extend my heartfelt gratitude to you for sparing your valuable time and sharing such valuable knowledge with us. We are sure that this idea you presented today will inspire new thought, research direction, and application in our professional journey. Once again, thank you, sir, for being with us today and making this session truly remarkable. Thank you, sir.
Okay, thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Okay, I'll leave it right now.
Thank you,
Okay.
sir.
Yes, yes, sir. Yes, sir. Yes, sir. You can leave now. Dear participant, kindly fill out the feedback for this session 4 now. Your feedback helps us to refine future session also. Okay, I will give you 2 to 3 minutes so you can put your feedback.